Okay, we are live now, actually.
Okay.
That was a different message. So, good morning, everyone, and welcome back. We are here for the first lecture of the day on unsupervised learning with Mihaela. So, Mihaela, please repeat, how do we say good morning in Romanian?
Bună dimineața!
Okay, that's great. Mihaela is a research engineer in DeepMind, and she's doing a lot of work on unsupervised learning, and she'll actually introduce herself a bit more. So thank you, Mihaela, for joining us.
Great, thanks, Jerica. So let me do this. So, hey everyone. I am Mihaela. I'm a research engineer at DeepMind and a PhD student at UCL. And today I'm super excited to talk to you about unsupervised learning. I'm very passionate about this field. And if I get you to be 10% as passionate as I am today, I think we're going to get very excited together. So, what is unsupervised learning? The aim of unsupervised learning is to learn structure from data. So what does that mean? Well, that can be a little bit vague. So perhaps the simplest way to think about it is to contrast it with some types of learning that you've seen before. So you've seen supervised learning before. And in supervised learning, we're trying to learn a mapping from input X to output Y. So our data set contains pairs. XY pairs from maybe high dimensional input such as an image of a dog to the mapping output label, for example, or one of 10 possible classes. This is a dog, this is a cat, and so on. And we have a lot of challenges. Here, generalization is one. If I see a new type of dog that the model has not seen during training, I want it to generalize and know, well, that is also a dog. And we also need to find a flexible enough parameterization. So in the case of a neural network, a powerful enough neural network to learn this mapping. Then there's reinforcement learning. In reinforcement learning, we are concerned with sequential decision making. So we're trying to learn behaviors that maximize rewards. So we have our agent. Our agent acts in a world that's often called an environment, and it's trying to find a behavior that will lead to maximal reward. And that has a lot of trade-offs between exploring new parts of the world that is never seen before, but also exploiting what it already knows. So this is one challenge, but there's also, again, the challenge of generalization. So how are we going to act in unseen states, for example? How are we going to transfer between environments? There's a lot of challenges with reinforcement learning, as you've seen, and you'll see in some amazing lectures through the school. Now then there's unsupervised learning, which again tries to learn structure from data. And the challenge here is that we don't have any labels and no rewards. So we don't have any additional input associated with our data. So in the case of supervised learning, we had the labels associated. In reinforcement learning, once we take an action in a particular state, we get a reward. In unsupervised learning, we don't have that. We have our data set that is a series of data points, and we're trying to learn something from that. But we still have some of the standard challenges of learning. How are we going to generalize? We want to go beyond the data that we've seen, of course. And we will have some other challenges as well. And I have a very small example here to show you that unsupervised learning is hard. So even in small dimensions, so things get often harder when we have higher dimensional data, but even in 2 dimensions, we can see the difficulty of unsupervised learning. So this is some data that I generated, and maybe we can answer the question, well, what kind of distribution could have generated this data? So you look at it and you think, well, this could actually be a Gaussian, not too bad. But it could also be a mixture of 3 Gaussians. So which one is it? Just by looking at this data, it's actually very hard to tell. And in practice, you will not be able to easily discern between the two, because I generated this data. I can tell you that it's actually a mixture of 3 Gaussians. So this is a very small toy example to show you that, yeah, unsupervised learning is hard. So one thing that you might say now is, why do we want to do unsupervised learning then, if it's so hard? Well, it turns out that unsupervised learning is a core building block for our products through super resolution, compression, text-to-speech. We use it to build better algorithms in science through drug discovery, astronomy, high-energy physics. And there's also the importance of unsupervised learning in other machine learning and artificial intelligence approaches. So we've seen reinforcement learning, and we're going to see throughout the talk a few examples of how unsupervised learning is crucial, sometimes to make a reinforcement learning work faster or solve a task that it couldn't before, by integrating these unsupervised learning approaches in reinforcement learning through planning, better exploration, and model-based RL, so learning a model of the world. And there's also different types of unsupervised learning. And the lines can be often blurry, but I just want to give a brief overview of some. So we've already seen clustering. So in clustering, we're trying to answer the question, how can I split the data? So how can I partition my data into different chunks, such as these chunks satisfy different properties, and different algorithms will have different properties requirements of their chunks. So k-means will say that I want my distance from my points to the center of the cluster to be as small as possible. There's also generative modeling. In generative modeling, we're trying to learn a model of the true underlying data distribution P star from a set of samples, which are our data set. So if this is our data, small 1D example, we're trying to answer, well, what kind of distribution generated this data? And there's representation learning. I don't think I have to convince you of the success and the importance of representational learning if you believe in the success of deep learning. So deep learning tells us that if we compose representations, that if we learn representations that are perhaps lower dimensional and encode more information in our models through the form of a prior. So for example, in convolutional networks, we are leveraging the fact that we know that we're using images, for example. Learning this kind of representations is easier than, makes it easier than for us to use this data in downstream tasks, such as reinforcement learning or supervised learning. But when I talk about representational learning in the context of unsupervised learning, I'm not talking about just using deep learning for a task. Specifically, I'm talking about learning representations, say in your learning pipeline, through an additional learning stage or integrating unsupervised learning in your learning. So for example, imagine that I want to do semi-supervised learning or reinforcement learning. Let's just briefly talk about semi-supervised learning because that's very easy. If I'm trying to classify what's in an image, I can do that by creating a very, very large data set and ask, for example, humans to label what's in each image. Or I can actually just label a subset of my data, which is cheaper. And then I can use the vast amount of unsupervised data that I have to build useful representations. And then I can do the supervised task just from these representations. And this is easier because we have a lot of unsupervised data out there. So if we think of all the images available, a very small percentage of those are actually labeled. So we're trying to increase data efficiency, so we have to label less data. Or again, perhaps help generalization, because if you have the kind of representations that encode semantic information, so for example, encode that there's a house here, there are some trees, and so on, downstream tasks are going to be easier. And not only in semi-supervised learning, but also in reinforcement learning. So if I go and see a new state and I can basically encode what's in that state in a more efficient way, then I can do more efficient decision making. And we're going to see some concrete examples of how this can be used in RL and how it can make a huge difference. So now that we say, okay, I want to do unsupervised learning, what do you have to do? Well, you have to find a few things. And the key message of this talk is that you have a lot of choices. And which choice you make depends on your end-to-end application and what you're trying to do. So this is broadly the case for any unsupervised learning approach. So for example, the first thing that you would have to do is to find an objective. So how am I going to train my unsupervised learning model? Then find a way to represent this model. Then find a way to learn the model using the objective that you've chosen. And that's not always easy, and we're going to see some example of that. And then you have to figure out how well you're doing. And especially in unsupervised learning, that can be pretty hard. So you have choices, and these choices aren't always easy. And to start with, let's look at a problem. And I'm going to focus on generative modeling as a case study, but this idea of choices and the trade-offs that you have between different choices is really applicable for all types of unsupervised learning. It's just easier to look and study one in detail for now. So again, generative modeling, you're trying to learn a model of the true underlying data distribution from samples. You have your data set here, and you're trying to answer the question, well, what kind of distribution could have generated this data? So one question you might already have is, why would I want to learn a distribution, and what would I do with it afterwards? Well, once you have a distribution, you can query it. If you have an explicit model of your distribution, so for example, if you have a density estimate of your model, so here you see that in the data we have a lot of samples here, we have a lot of samples here, so this is a reasonable model. We can then ask, well, is it likely that this point also comes from the same distribution as the data? And the answer is no. I haven't seen any data here, and I can query this probability distribution and ask it for the likelihood that this data comes from the same distribution. And it's going to tell me, no, I have no mass here. So this can be very useful for a lot of things, including outlier detection, and we're going to see some examples of this, for example, in reinforcement learning as well. Another thing that you can do with a distribution is sample from it. And depending on how you represent the distribution, that can be easy or quite challenging. But the key idea behind sampling is generalization. So here I show an example where we have our data. This is the same data that we've shown on the left, but now we generate model samples after we've trained our model. And the crucial part here is that these samples look a lot like the data in that they have the same statistical properties, but they're not the data. Because if I just wanted to sample from the data, I would use a hash table. So I wouldn't go myself through all the trouble of doing generative modeling. And just a very intuitive example here is a data set of faces. If I train a generative model on a data set of images of faces, just like a picture of me, for example, and many others, when I make when I sample from my generative model, I then wanted to generalize. So I wanted to, well, we often use these words like understand, but statistically, I wanted to be able to model the distribution and generalize enough that it can generate a new face. So a face that looks like a face of a human. So that means that it captured the statistical properties of the data, but generalized. So I don't want it to just show me some of the faces that it's seen before. And while I'm not going to stress this a lot in the talk, you also have a choice of how you want to represent your data, as discrete data or continuous. Sometimes it's more clear than others that, oh, I want to do the discrete and continuous, but sometimes you also have a choice. And what algorithms you can use downstream can be affected by this choice. So for example, images can be modeled as continuous between 0 and 1, but also as discrete with pixel values between 0 and 255. Then there's also health data that can be continuous or discrete. So for example, someone's age, you can make that to be, for example, a floating point number. It can be something discrete. I'm just going to round to the nearest integer. Some types of data are more inherently discrete than others. So for example, text is quite discrete. But again, even before you start looking at the algorithms, you also have to start looking at the data and figure out which way you want to model it. So now let's look at the first important choice that you have to make if you want to do generative modeling. And that is the choice of the objective. So we said that we want to learn a model of the true underlying data distribution. So we will have the true distribution throughout the talk is going to be represented as P star. So this is the true unknown distribution. And the model is going to be represented as P theta of x. Theta are the parameters that we're going to learn. So if we learn a Gaussian, for example, theta are going to be the mean and the variance or the covariance matrix of the Gaussian. But if I'm going to learn something using a deep neural network, theta are going to be the parameters of that neural network. And what we want to do is to find the loss function that tells us that, well, if my data distribution is here and if my model distribution is here, then, well, you're not doing a good job because you're far from the distribution, but also the kind of loss function that will give us the right gradients to move into the direction of the data distribution. But things are even a bit more complicated than that. We don't have access to P star. If we did, we wouldn't be in the generative modeling game. So the picture actually looks like this. I have my model. Sometimes I have the explicit distribution associated with my model. And I have my data. So we have to find the types of loss functions that we can evaluate only using samples from our true distribution. And there's a trick that allows us to do that, and that is Monte Carlo estimation. So we will use the kind of objectives that allow us to incorporate the data distribution only through expectations. So we will, every time we have an objective, try to look for objectives that look like this. So we have an expected value of under the true data distribution of a particular function. So this is the integral of P star of x, f of x dx. And we estimate that using the Monte Carlo estimate, which is the empirical mean of the function evaluated at samples from the true distribution, which is great because we have samples from the true distribution. This is our data. So if you depend on your data distribution through samples, we're good. If you depend on it somehow else, then you might be in trouble. And we're going to see some example of that in a bit. So now that we've seen that we want to find the type of loss functions that tell us how far two distributions are, we can look in the mathematics literature and see if we can find some. And turns out there are plenty. And specifically, these have to satisfy certain mathematical properties. And we're often going to be concerned with divergences and distances. And they have different mathematical properties to satisfy. But one that is important for us is that if the distance or divergence between two distributions is 0, then the two distributions are the same. So this is quite a powerful thing to have, and it gives us some guarantees about the loss functions that we're using. And one really common divergence that is used is maximum likelihood, or sorry, the KL divergence, which leads to maximum likelihood. You've probably seen it as maximum likelihood before. So the KL divergence between distribution P star and P theta is defined. So this is the definition of the KL. The expected value under P star of the log ratio between P star of x and P theta of x. So now if you paid attention to the Monte Carlo estimation importance bit, now you're already flashing a bit and say, oh, okay, but actually we depend on P star here, and it's not in the expectation. So that might be problematic. But we're lucky. It's not problematic because the log of a division is the difference of logs. So we're going to separate these two terms. And the first term is only going to depend on the true distribution. It's the negative entropy of the true distribution, which we don't have access to and also don't want to change. We don't want to change the true distribution. That's something that we don't have and we want to model. And then the second term is the expected value under the true data distribution of the log probability of the model. So now we're good because this is the model. We will know the model. And this is the expected value under the true data distribution. So we can use Monte Carlo estimation. So every time you see something that looks as maximization of this expectation, because here we have a minus. So even though we started with a minimization of divergences, we ended up with the maximization of this expected value. This is what's happening. We're minimizing the KL divergence between the true distribution and the model distribution. And what this tells us is extremely intuitive. It's saying that I want the model which assigns high likelihood to samples from the data. So I want the model which can explain my entire data set. One thing that you might say now is, well, if all divergences have this property that if they're 0, the two distributions are the same, why should I be concerned with multiple divergences? Well, it turns out that there are a lot of trade-offs associated with which divergence you use, because in practice, you will not have a powerful enough model to truly learn the data distribution. So let's look at a very simple example. Our true distribution here, P star, is given by a mixture of two Gaussian distributions. So this is our data. It has two modes here. Our model is going to be a Gaussian distribution. So we're learning the mean and the variance in this case because we're on one dimension, sorry. So now we're trying to say, well, okay, our model is not powerful enough to learn the true data distribution. So what will happen if I fit a Gaussian to this data? And what will happen if you fit it using maximum likelihood, so the KL between P star and P theta, is that the model is going to spread a lot of mass in between the two modes. Why is that? Well, we've said that maximum likelihood tries to account and explain for every single data point. So we're going to have data here, we're going to have data here. How can a Gaussian put mass on both of these, where it's going to put mass in between as well? Which is not really great, because now if I ask the model, is it likely that I have data here? It's going to say, oh, it's so likely. In practice, we have no data here. Now, if we use the reverse KL, so important here, the KL is not symmetric. So if I use the KL between the model and the data, then the model no longer has to explain the entire data set. It just has to generate samples that are that have high likelihood under the data distribution. So what it's going to do is just going to focus on one of the modes. Is this better? Well, now it's completely ignoring parts of the data. So now if you're asking it, is it likely that I have data here? It's going to say, no, I don't know what you're talking about. But there is data here. Which one of these is right? It's unclear. It depends on your application, and it depends on what you're trying to do. And it's also important to stress that this is not only a theoretical and nice exercise. In practice, even though your data distribution is going to be more complex than this, and so will your model, you don't know how complex your distribution is and how complex your model has to be. So, for example, if you care about sample generation and generated good sample quality, maybe you focus on one. If you care about really explaining parts of the data, you focus on the other. And there are other divergences as well. So, for example, the Jensen-Shannon divergence is a mixture of the two KLs. So maybe you would think, well, we get something in between. Though in the case of the example that I've shown you before, what happens if you train a Gaussian distribution to minimize the Jensen-Shannon between these depends on initialization. So this is another important idea, that model initialization really matters. So if I initialize my Gaussian to be somewhere in between the two modes, what it will do is it will do the maximum likelihood solution. Now here, in this right-hand side corner, what we see is that if I initialize my model very close to one of the modes, it's going to do the reverse KL solution. So there are other divergences. They have different properties. So the take-home message so far is that given a model family, different divergences will lead to a vastly different distribution. So it's really important to know these trade-offs, because you will choose them based on your end-to-end application. But so far, I've made things sound a little bit easier than they actually are. So remember the Monte Carlo estimation bit that I was talking about. For the the forward KL, we saw that that's easy. We ended up with a constant and the maximum likelihood objective. We're all good. Now, I also showed you a few plots with the reverse KL. But the reverse KL is not that easy to optimize. So if we look at our definition of the KL, now because we've swapped the arguments, we have expected value under the model of the log ratio between the model and the data distribution. We apply the same trick, split the ratio into a difference, and now we have the first term is the negative of the entropy. And in general, evaluating entropies of high dimensional distribution is quite challenging, but this is not even our problem here. The problem here is that the second term requires access to the true data distribution, which we don't have. So one question that you might have is, well, Mihaela, how did you do these plots then? Well, I cheated. I actually used the true data distribution here when I created the plots for the reverse KL and for the Jensen-Shannon, which in practice you don't know, so you won't be able to do. So this really motivates us to look beyond divergence minimization, or maybe find a way to do something with the Jensen-Shannon without directly accessing the true data distribution, which we don't have. And turns out we can do that somewhat approximately by looking at two-player games. So now we're going to look at a completely different way to train generative models. And this way involves the following players. We have a discriminator. This model learns to distinguish between real and generated data. So if this is the real data and this is the fake data generated by the model, the discriminator has to say, well, this is real, this is fake. And it does this for different samples from the data and from the model. The model, in this case, often in this literature, is called generator, so I'm going to call it that, but this is the same model that we were talking about before with parameters theta that we're trying to learn. It tries to generate data that fools the discriminator. So it's this cat and mouse game. And if we look at it perhaps a bit more concretely of what these models, which are often called generative adversarial networks, do, we can look at the following scheme. We have our discriminator. We train that to answer the question, is this real or is this generated? So we train that really well. We, let's say, do multiple updates, perhaps, to distinguish between them. Once the discriminator is trained, we can tell the generator to for example, update its parameters to generate data that's so good that this improved discriminator now can no longer tell the difference. So the intuitive idea here is to say, well, the discriminator improves. Then the generator has to become better to fool this discriminator. Then the discriminator has to become better to distinguish between data and sample. So it's kind of this intertwine between the two players. Now, if we think about this mathematically, the original objective introduced in the original GAN paper looks like this. So now we no longer have only a minimization with respect to theta of a divergence, like we've seen in the KL case, but we also have a maximization from the perspective of the discriminator. So this is our mathematical way to formalize the cat and mouse game. Whatever the discriminator gains, so phi are the parameters of the discriminator and theta are parameters of the generator, whatever the discriminator gains, the generator loses. Great. But what the discriminator is trying to do when it is trained is to maximize the probability that it predicts that real data is real, and maximize the probability that it predicts that generated data is generated. Once the discriminator has been well trained, the generator now has to train with the same loss function, but with a different sign. So this is what the difference between min and max is. Now the generator is saying, well, I want to learn theta such that this term is as small as possible. So that means that the discriminator predicts that generated data is real. So now going back to this idea of divergence minimization. Are GANs doing divergence minimization, and how is this related to the fact that we saw that optimizing the Jensen-Shannon directly is impossible in practice? Well, in the original GAN paper, the author showed that if the discriminator is optimal, so this is a big if, and I'm going to come back to this later, but if the discriminator is optimal, so if we train a perfect classifier to distinguish between data and samples, the generator is minimizing the Jensen-Shannon divergence between true and generated distributions. And this also gives us the connection to optimality again. If the divergence is 0, then the distributions are the same. And if we look at this nice objective here, it has the property that we want. We only depend on the data distribution through samples, which is really neat. So this is a nice way to solve the problem requiring the actual knowledge of the distribution in the definition of the Jensen-Shannon. Now, things are not that simple, and we're going to look at this later on, but I think it's important to know. So can we then use this approach, this min-max cat and mouse game, to train models that minimize other divergences and distances? And the answer is yes. And I'm just going to give one more, which is the Wasserstein distance. So this is a distance, not a divergence. It's symmetric this time. And one thing to notice straight off the bat is that to estimate the Wasserstein distance, you need to do optimization. So remember when we talked about the KL divergence, there was no maximization or minimization in the definition of the KL. It's an expected value of a log ratio. Great. Here, just to find out how good we're doing, so without thinking about training theta, just to find out how good we're doing, we have to optimize over a class of functions, and specifically a class of functions that's called one Lipschitz. So the difference and the absolute value of the function difference has to be smaller than the norm of the difference of the argument. So you can't move too much. The function has to be relatively smooth. So we optimize over this class of functions to do what exactly? Well, we've seen how we can use classifiers to separate, in some sense, the data and the model. Now we're going to look at differences of expectations. So what this is telling us is that I want the difference between the expected value under the data distribution of F and the expected value under the model distribution of F to be as large as possible. Subject that F is relatively smooth. So let's look at a simple example, the same example that we've seen before. We have our data samples here. We have our model samples here, and we're trying to separate these as much as possible in expectation using a function F. Now, it turns out that in this case, F star looks like this. So we're making F positive under the data, negative under the model, because this is a relatively simple example. Then the difference between the expectation under the data and this expectation under the model is going to be positive and relatively large. Now, the reason this one Lipschitz is important is because it stops me from doing this. I can't grow too fast under the data and then make this difference really, really large. So the reason I don't have bigger bumps here is because of this one Lipschitz constraint, which is really, really important. Okay, so this is the estimation of the Wasserstein distance. How about learning? So now we're trying to learn our parameters theta to minimize this divergence. And voila, we end up with something that looks a lot like what we've seen before. So we have the minimization with respect to our model parameters. And now the supremum over class of functions is intractable in practice. So what we're going to do instead is we're going to say we're going to parameterize this class of functions using neural networks, and we're going to somehow regularize that to be one Lipschitz. And then the objective is the same as the difference in expectations, only that I've replaced F with our discriminator. So now this looks a lot like a GAN. And it is a GAN because now we have this two-player game. They have different signs. So again, the cat and mouse game is present here. And moreover, this allows us to do something that just looking at the Wasserstein distance would be very difficult. So again, at each time step, we cannot optimize the discriminator or the critic here, F, to optimality. That is just intractable. So what GANs allow us is to look at these objectives and say, okay, I can't do exact Wasserstein distance optimization in this case. That's intractable. So instead of doing this optimization fully, I'm just going to do a few gradient descent steps on phi, and then I'm going to update theta, and I'm going to keep playing a little bit like this. So this is to say that in practice, the discriminator isn't optimal. So you have limited computational resources. You can't just train D to optimality every time you update G. And even if you did, we don't have access to the true data distribution, just some samples from it. And moreover, your critic, your discriminator, is bounded by the power of the function approximators that you're using. So even though neural networks are very powerful function approximators, they're not going to be optimal. So this tells us that in practice, GANs are not doing divergence minimization. So we have this nice connection with the Jensen-Shannon, with the Wasserstein, but when you train a GAN in the wild, you will not be doing that unless you have, let's say, a very, very toy example. But there's another way to think about discriminators and losses that will make it quite appealing to have this property. We can think of discriminator as learned loss functions. So from the perspective of the model or the generator, we have a minimization with respect to the generous or theta parameters of something. This is something that also the KL has. We minimize with respect to theta something that's a divergence. The difference here is that the something is learned. So why is this important? Well, first, we've seen that learning things is good. We've seen that in deep learning, that, for example, we can embed into our models, that if we're learning models of images, we can use ConvNets and so on. Now we can take this one step further, and we can embed that information about our data into our loss, which is pretty awesome. So it allows us to say things like, well, the discriminator will have this neural architecture. So for example, it will use a ConvNet, because that will allow us to better focus about certain aspects of the data that we care about. So for example, in images, edges are important, and ConvNets really care about that. So why not put that into our loss? And this is what this kind of two-player game allows to do. So to build more knowledge that we have about our data, not only into the model, but only through the loss function as well. So what should you be doing in practice? Again, you have choices. I can't tell you which one is right or wrong, because it depends on what you're trying to do. GANs can produce really good samples, and this idea of learn loss function, I think it's very appealing to many, but they're harder to analyze and can be more unstable to train. If you do divergence minimization, it's easier to analyze and know what the loss is doing, but it's harder to get good samples because you don't have this extra knob to tell the model what to focus on. And we're going to take a break for questions now, and then we're going to talk about how to represent our models.
Okay, great. Thank you, Mihaela, for this great first segment. I will just share now the screen to show the questions. We do have quite a few questions.
Oh, that's great.
Can you see the questions?
Yes. Shall I start
okay.
about? Shall I start?
Yeah, I can just read the question so that. So the first most popular question: what is the difference between unsupervised and self-supervised learning?
Oh, that's a very good question. So what is the difference between unsupervised and self-supervised learning? Self-supervised learning is a type of unsupervised learning, but I would say that not every unsupervised learning is self-supervised learning. So at least currently, self-supervision is actually a really, really important idea in specifically in representational learning, that allows us to use supervised learning to do unsupervised learning, which is amazing. So for example, imagine that I'm trying to learn representations of images. That is very hard. You can do that by doing generative modeling, but generative modeling itself, as we've seen, is very hard. Perhaps you can define the right task that allows you to use supervision to learn these representations. So one example is colorization. If I have an image black and white, and I learn to color that image using my model, perhaps it's going to learn the right representations, and I can build this task to be supervised, even though I don't have supervised data.
Thank you. Purely unsupervised learning is not feasible. There's no free lunch theorem, no inductive bias, no learning. What is your take on this?
Oh, that's an excellent question. That's one of my favorites. I think this is, in some sense, the key message of my talk, is that you have to build the kind of information that you have into your objective, as we've seen so far, into your model, and use that. There is no, the fact that there's no free lunch tells us there's no absolute right choice, but you can basically specialize in what you're trying to do and do that a little bit better.
Right. If we understand the distribution of our data, is it reasonable to use it for data augmentation?
Yes and no. So it depends on what you mean by understand. So generative modeling allows us to generate new data that looks like our data distribution. So in practice, yes, this is very appealing to train a generative model and then use that for semi-supervised learning, for example. I think that's just very hard so far, because it turns out that generative modeling is a bit harder than classification. So if you have enough data to do classification really well, like your generative model might not be good enough, and there are some really good papers that I can point you to that look specifically at this.
Can unsupervised learning be used as an instrument for feature selection? For example, multiple clustering and select the features that led to best clusters.
Yeah, it can. And I think in some sense, this is what also representational learning does, right? It is doing feature selection, and we are providing the right types of losses to kind of do that.
How is unsupervised learning applied to text-to-speech?
So I think text, in some sense, is a great candidate for unsupervised learning because just the raw representations of text are quite bad because they don't encode any semantic information. So if I get a dictionary and I try to represent that into a computer, I'll probably say, well, the first word is 1000. The second one is 01111. Well, this encodes no semantic information about the data, which will make it hard for me to learn end-to-end applications. If I use unsupervised learning and I build the kind of representational learning for text, then I can then use that for a lot of other applications.
What's the difference between representation learning and learning embeddings?
I think there's also a matter of terminology. So some people call them embeddings. I think embeddings are often used for text from the text literature, but yeah, I'm not sure if I can answer this a little bit better.
Please compare variational autoencoders and generative adversarial networks. Maybe this is coming.
Yeah, maybe we can do this a little bit in the second part of the
Right.
talk.
Okay. Does pre-training a model with unsupervised learning like autoencoding before doing supervised learning helps?
So yes, well, maybe not the same model, but I think there's a lot of evidence right now in the progress that we've seen in the last 2 years is actually amazing in semi-supervised learning, building representations using unsupervised learning and then doing supervised learning. And as someone mentioned before, self-supervised learning is a way to do that very successfully.
Maybe we take 2 more questions. KL difference focuses on minimizing difference of expected values between model distributions and samples. Isn't it a problem that it ignores variance?
The KL divergence, so what do you mean by that? Because in the terms of differences of expected values, this is what we saw for the Wasserstein distance. I wouldn't say that the KL divergence generally ignores variance. So for example, we saw the case of the Gaussian distribution and the bimodal data, but maybe I'm not understanding the question, and I'm happy to take this offline just to make sure that we can answer this right.
Yeah. Maybe just one more. Do you think studying unsupervised learning? Yes. Do you want to?
Yes. The answer is yes.
Okay.
And I think just one thing to say is that a lot of what I'm talking about today is the core principle, I would say, behind machine learning, because we are always learning probability distributions. I talk about maximum likelihood. If you're doing supervised learning, you're often doing maximum likelihood. It's the same idea. This is why I study unsupervised learning, is because I want to understand machine learning. And this is a way that I found that's really, really useful to do that. And we'll see later on that, for example, how you learn these models is related to RL. And all of these things are very, very related.
Okay, great. So maybe we move on to the next segment. So also answer more questions offline.
Yep. Sorry, Vivek, I think I couldn't hear you for a second. Can you just say that again?
So I was just saying that we will, because there are still many questions unanswered, we will make a document, and when you have time, you will answer those offline.
Absolutely.
We will also have another short break at the end to take a few more questions.
Yeah, absolutely.
So please keep posting questions in Slido.
Yes, please do, please. Okay, so I'm going to start presenting again.
Yes.
And then I'm going to go back to... Okay. Can you confirm that you can see again?
Yes, this is fine.
Okay, perfect. Thank you. Okay, so we so far talked about the choice of objective, but I'm going to bother you with a few more choices by the end of this talk. And the next one is the choice of model. So how are we going to represent this distribution that we're learning? And we've already seen the importance of the model in a very simple maximum likelihood example that we saw, with the data being bimodal and the model being unimodal. So this is not really what we would want to have in practice, because now we have a lot of mass of our distribution here. This is not great. Now, if our model is too powerful, we have overfitting. So overfitting is also a problem in generative modeling, not only in supervised learning. So the standard, let's say, symptom of overfitting is that we're not putting mass in between similar data points. So for example, if I have a really, really powerful model that just sees some data from these modes, it's just going to put some mass on the data that is seen. So then if you ask it to generate data, it's going to just give you the data set. So it's going to be, let's say, a parameterized hash table, which is also cool, but not what we're necessarily interested in. So we want to be somewhere in between. And the challenge here is that we don't know where we want to be. So again, there's no, as someone said, there's no free lunch. You just have to figure out, based on what you're trying to do, how to go somewhere in between these two. And broadly speaking, we're going to go into some concrete examples later on. You have two main choices. The one is between explicit and implicit models. So are you modeling the density directly, P of X? So are you having a density estimator? Then you can answer questions such as, is it likely that this other data point comes from my distribution, and so on. Or you can just say, I don't want to model the density. I don't want to answer this question. I want to generate new data. So this is what's an implicit model. You will not have what an implicit model does. You will not have access to P of X, but sampling will be easy. So often, modeling P of X can lead to difficult sampling, or it might restrict you to a particular family of distributions that you don't know beforehand. The other big choice that you have is whether or not to use latent variable models. So usually when we have our data set, let's say a data set of images, we have some high dimensional space, we can model that directly. We're going to see some examples of that later on. But intuitively, we can also say, well, this data is really high dimensional. There's no way there's mass everywhere in the space under the distribution. So for example, if we think of all possible images, so not natural images, just all possible combinations of pixel values, that's just a huge number. The number of images that make sense is very small. So it's intuitively, in comparison to this number, of course. So it's intuitive to think that our data lies on the lower dimensional manifold, and then we can transform the lower dimensional data into a high dimensional space. So this is the intuition behind latent variable models. The reason they're called latent is because no one tells you what Z is, what your latent variable is. So this is not supervised learning. You're introducing this to aid you in learning. So you're mapping from a lower dimensional space, Z, let's say something like 100 dimensionals, often for images, something for which you can choose a prior distribution, so something like a Gaussian would do, and then you transform that using a function, which can be either deterministic or probabilistic even, and we're going to see examples of these in a second, and then you're going to go to your higher dimensional data. And I think it's important to stress a bit this idea behind latent variable modeling and why would you want to do it. So let's look at an example of a face here. The background takes a lot of the space and it's extremely correlated. All the pixel values are black. So it's intuitive to think that we will have a lower dimensional representation of this image that then will allow us to go from from Z, from our latent, to our high dimensional X. And there are a few attributes that we as humans can assign that make sense: hair color, eye color, blah, 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 to generate our X. But in practice, it's important to stress that no one tells us these. So this is just a kind of a human aid for us to understand this. These are just samples from a prior. It can happen, and it does happen sometimes, that the model assigns some say not really meaning, but groups latent variables in certain way. But that's just because it's statistically efficient for it. It has no reason to think about them in any other way. And the challenge here is that, again, no one gives us these factors. We are learning everything unsupervised. So we're learning a mapping between Z and X fully unsupervised. Why would we want to do that? Well, sampling is cheap. We are going to use what's called ancestral sampling. So we sample from Z, we pass that to our transformation, and we get our data X. So if you care about sampling, this can be good. There's another reason why this can be good. If you care about representational learning, so someone already asked about variational autoencoders. What variational autoencoders do is they learn generation and inference jointly. So what inference is the process of inverting this generation mapping. So in generation, we go from low dimensional to high dimensional. In inference, we go from high dimensional to low dimensional. And then we can use this for representational learning for downstream tasks, such as in supervised learning and so on. And we're going to see examples concretely of this later on. So now that we've looked at the big two choices that you have, again, explicit models, so do I model phi theta of x directly, or implicit models, or latent or observed variable models, let's look at some concrete examples. So what can you do as the unsupervised learning practitioner? Well, the first thing you can do is to use canonical distributions. So if I can say, well, I'm going to use a Gaussian distribution. Now, we can try to then learn the parameters theta. They're going to be the mean and the variance of our distribution. This is nice because it's easy to learn. So for maximum likelihood, we have closed form solutions. That's quite nice. But we already saw a problem with it not being expressive enough in 1D. In multiple dimensions, certainly if we talk about images, images are not Gaussian distributions. So we want to build more and more expressive distributions that go beyond this the simple canonical distributions. And perhaps the simple way is to go to mixture models. So mixture models already will solve the multimodality problem. And what mixture models say is, well, I'm going to learn a weighted sum of probability of specific mixture components. So these pi k's will have to sum to 1. Then this is a valid probability distribution. And these individual components I can choose myself. So they can be both individual Gaussians. And now I can model things like this. Things that we've seen that Gaussians cannot do. So the challenge with this, though, is that we have to choose k in advance, which can be cumbersome. Also, too large k can lead to overfitting and so on. But they're very, very important, a very important class of models to know about. Then there's autoregressive models. So autoregressive models use the product rule of probability to learn distributions. So what is the product rule of probability? I think it's quite intuitive. Imagine that I have a sentence. What's the probability that I see the sentence in English, for example? Well, it's the probability that I see the first word times the probability that I see the second word given the first word times the probability that I see the third word given the first two, and so on until the end of the sentence. This is incredibly expressive. And what we're doing when we're learning autoregressive models is to learn parameters theta that now model the conditional distribution of a particular, let's say in our example, word, given what we've seen before. And this conditional distribution, for example, often shares parameters. So if you have something like an RNN, you will share them between these different time points. You would share parameters. Now, there are some challenges with autoregressive models. One of them is that sampling can be expensive. So how would I sample then a distribution from this, a sentence from this distribution? Well, what I would do is I sample the first word, then I sample the second word given the first word, and I keep moving. The problem is that this is linear in sentence length. So this can be quite expensive. There's also the choice of ordering. So this is valid for any ordering that you choose, and it's not inherently clear which order is better, for example, for images. Do I go left to right to left, and so on. Now, there's another type of explicit model that is very powerful and uses the change of probability formula. So we've already seen the product rule of probability. Now we're looking at another trick that we can use to define complex distributions. And this one now introduces an auxiliary variable. Here I'm going to call this x. This auxiliary variable, you can think of it as a latent variable, but it doesn't have the same intuitions that I've talked about before in terms of the lower dimensional space, because x and y have the same dimension. So we're just learning to transform mass in a high dimensional space. And the way we specifically do that is using invertible functions. So if I have a random variable x with, let's say, a Gaussian distribution, and then I transform that using an invertible function, what's the probability distribution generated by that transformation? Well, the probability that I see a certain y is the probability that I see the x that generated my y under its original distribution. So if the x is here, what's the probability that I see the x under this Gaussian, times the determinant of the Jacobian, which tells us about the change in volume that the transformation gives us. So now things are great. We can go from simple to more complex distributions. I think a very intuitive example to give is the classical one-dimensional example of the CDF, or the cumulative distribution function. So we know that if our input or our random variable x is uniform between 0 and 1, I can actually go from that random variable to any random variable in one dimension by using the inverse of the CDF. So this f theta here is going to be the inverse of the CDF. This is quite a powerful tool. Now, there's some challenges here. What are we learning in this case? We always have to answer the question, what are we actually learning? What we're learning is the invertible function. It will have some parameters theta. Ideally, we want to use neural networks. Well, that's a bit hard. Turns out neural networks are non-invertible. So not only that, you want them to be invertible, you want both f and f inverse ideally to be easily computable. Not always that's the case for all flows, but f, importantly, mathematically needs to be invertible. And we also want to be able to compute this determinant of the Jacobian cheaply. But there is something that comes a bit to the rescue, even though we have these difficulties, and that's that flows are composable. So how awesome is that? That we can start with a very simple distribution. So for example, something like a Gaussian distribution that is unimodal, like we've seen in the case of 1D examples, and now we're looking at 2D examples. If we transform it using a simple planar flow, well, the mass has changed a bit. If I stack 10 flows, now I have very multimodal distribution. It has some mass here, it has some mass here, some here. That's quite powerful. Now, the same if I start with a uniform distribution. If I keep transforming that, I get very, very powerful distributions. So this is the key idea behind flows. It's often hard to make f theta very, very complex in its own, but we can compose it and kind of build quite complicated models that way. So while flows are a very nice model, the latent variable that we introduced is of the same dimension as the data, and we have transformed that latent variable using an invertible function. But sometimes we might want two things. We might want to have our latent variable being lower dimensional for all the reasons and the intuitions that I've already talked about. And we might want to have a non-invertible mapping from our latent to our observed variable. So specifically, we might actually want to have a distribution, a conditional distribution. So just like we've seen in the autoregressive case where I conditioned the third word on the first two, now I condition my entire output, so my image, on the latent variable. And that's what I model, and that's what I learned. This is where my parameters are. Excuse me. So one possible it's just another way to think about this is that, well, if I have a set of latent variables that, for example, encode all the semantic information about, let's say, faces, then I can perhaps generate a few faces with those latent variables. It need not be a one-to-one mapping. And I can then generate and use that distribution. Now, there's a catch. We've seen the product rule of probability. Now we're going to use the sum rule of probability. So now we have this conditional probability. We have to answer the question, well, what's the marginal probability that the model assigns to a data point. So if I have a new image, what's the probability that the model assigns to that image? And that is given by the sum rule of probability as follows. So intuitively, to be able to assign a particular mass to one image, we have to look at the chance for all possible z. So this is what this is telling us. The integral is that the chance of seeing that z under the prior, which we can choose again here, it would probably be something like a Gaussian, times the probability that that latent variable generated our data point. So this is intuitive. For all possible latents, how likely is it that we see them multiplied by the chance that our data point was generated by that latent? There's a huge catch though. This integral is intractable for complex models. So if you have something complex here, you won't be able to do this in practice. You might have seen models such as factor analysis where you can do this, but for complex models, we won't be able to do this. But we can try to get around it a little bit. So instead of looking at p theta of x directly, we can apply Jensen's inequality and find a bound on log p theta of x, which we can then use to train our models. I'm not going to go about this in a lot of detail, but there are two main points that I want to stress about these models, which are often called methods which do variational inference, and in combination with neural networks, these are called variational autoencoders. The idea here is twofold. One, we're looking at approximate methods. So we won't have access to exact to p theta of x because this integral is so expensive. And we've introduced inference. So remember, I talked about inference as the way to map from our high dimensional space to our low dimensional space, and that we can use this for representational learning. And this is what this does. We've introduced a new model with parameters eta that we're going to learn that learns the inverse mapping. So going from x to z, and is trying to explain our data that way. One thing that you might say though is, I don't want to deal with this very complicated integral. I just care about sampling. In that case, you might say, well, fine, you give something away. So this is not something that comes for free. You no longer have access to an explicit distribution, not even in an approximate way. But you can have a deterministic transformation, for example, from latent space to observed space that now just produces samples. So on the output here, you no longer have a probability distribution, you just have ways to generate data. And again, because you don't have this probability distribution, now this restricts the set of objectives that you can use for training. So you won't be able to use maximum likelihood, for example. Okay, so we've talked about choices of objectives. We've talked about choices of models. We haven't talked yet about how to combine them or how to learn these models. So we often want to learn using gradient descent. Gradient descent is great. It allows us to do backprop and neural models. But often we kind of sweep under the rug that what we're doing is Monte Carlo estimation of the gradient. So for example, what our objective is the expected value. So sorry, I'm focusing on maximum likelihood for now. So the maximum likelihood objective is the expected value under p theta of x, p star of x, this is important, p star, not p theta, of the log p theta of x. So this is what we're trying to learn. Great. Now we're trying to find the gradients with respect to our theta of this expectation. But we're lucky. This is not problematic because p star of x does not depend on theta. So it turns out that in that case, we can swap the gradient and the expectation, and we can use Monte Carlo estimation here. So we're using Monte Carlo estimation not to approximate the objective only, but also the gradients themselves. So what we do is for example, let's say use backprop to compute these gradients, and then we average over a set of samples. So this is all good, and this is what we do in practice all the time. But sometimes things are a bit more messy. So we have sometimes the gradient with respect to theta, so our distributional parameters, of an expectation with respect to the model itself of a particular function. Now we cannot put this gradient inside the integral easily anymore. We would lose, the gradient would be 0, we will have no gradients. But so one thing that I first want to say is that this is important. This is not a purely intellectual and mathematical exercise. We've already seen this. We've seen this in the GAN case. Remember, we had expected value under the model of something that the discriminator assigns to the samples. So, and we're trying to learn these parameters. And we've also briefly seen it in the explicit latent variable case, where we use the bound on the maximum likelihood, so the approximate explicit latent variable models. So we really care about this. And not only do we care about this in unsupervised learning, we also care about this in reinforcement learning. So in reinforcement learning, your objective is something of the form of expected value under the policy of, let's say, just quickly, the value function of the S0, right? But you have an expected value under the parameters that you're trying to learn. You're trying to learn the policy. And this kind of same challenges apply in unsupervised learning as they do in RL. And the solutions are often the same. So the one solution that we might use in unsupervised learning, and that's very used in RL as well, is the score function estimator, or reinforce. It's very general. It makes very few assumptions on the cost and the probability itself. It can be used both for discrete and continuous data. This is why it's very applicable in RL as well, because there you have, sorry, let's ignore that noise. So we have discrete and continuous data, and we can then apply it in RL. So we also have the pathwise estimator, which assumes that the cost has to be differentiable, and it makes more assumptions on P, but it's often better in practice because it's low variance. It need not be, but sometimes it is. So the score function estimator, while it's very broadly applicable, can lead to unstable training because of its high variance properties. And another type of estimator is the measure valued estimator, which makes very few assumptions on the cost, but is computationally expensive. And this is why it's not very used currently in machine learning. So the key take-home message here is that we're interested in Monte Carlo estimators, not only for the loss, but also to estimate gradients in training. So we've seen that in the maximum likelihood case, and also what these estimators are doing, the score function, the pathwise estimator, they're just doing different tricks to get to Monte Carlo estimators for gradients. So this is quite important. So now that you've become, and you're going to become, an unsupervised learning expert, you're going to read a lot of unsupervised learning papers. And what they do is they present a choice of objective, model, and learning choice. So how are they learning their parameters? And once you've read that paper, a particular paper, you need to be able to answer this question. So how are they training your model? What representation are they using for their distributions? And how are they updating their parameters? And let's look now at a few combinations between models and learning criteria and how amenable they are to different updates. So we've seen maximum likelihood. It has a log, it has an expectation under the data and a log probability under the model. And we've seen that you have different types of explicit models. So because the maximum likelihood objectives requires an explicit model, it requires p theta of x, models that are explicit are often trained by maximum likelihood. It need not be the case, but in practice, this is a very fruitful combination, for example, through approaches that use autoregressive models that are trained by maximum likelihood. So one set of examples is given by Pixel CNN, Pixel RNN, have been used on image data, WaveNet which has been used on audio, GPT, which is a very powerful model trained on text. And the difference that lies between these models is they use autoregressive models, they train by maximum likelihood, they use the same gradient estimation, but the difference is how they parameterize the model. So the kind of inductive bias that you put into your model to train it. Now, another fruitful combination is using implicit latent variable models and GAN training. So far, I've shown GANs as using this objective. So we optimize with respect to theta. So we minimize with respect to theta. We maximize with respect to the discriminator parameters, these two expected values. Now, here we have an expected value under the model. This doesn't tell us whether the model is explicit or implicit. We know that this is a bit difficult to learn sometimes because of the gradient estimation problem. But often you will see the GAN criteria written this way. So now you no longer have X here, you have a prior Z. So we've introduced latent variables. And specifically, you are assuming that you're going to use the pathwise estimator because now you'll be able to switch the order easily between latents, between the expectation and the gradient. So you're able to train your model. And that you have an implicit latent variable model. So you don't have a likelihood, you don't need it for this objective. So while often GANs are written like this, they need not be implicit, and you need not use the pathwise estimator to train your GANs. So there is, again, a bit of a confounding between the objective, the model, and the learning principle. So now you've done all this work. You've done your homework. You've looked at the model objective, the objective, the choice of model, the choice of learning principle, and now you want to see how well you're doing. Well, it turns out that it's really hard in unsupervised learning. So generally, we don't have any metric that is able to capture all the properties that we care about, such as sample quality. So you want to generate good samples. You want to generalize. So you want to go beyond the data that we've seen. You also want to use this for representational learning. In practice, people try to use likelihoods, but that's not really a good idea, and there have been problems with that. But also, that excludes comparison with implicit models. So we want then to perhaps use something else to evaluate our models. And there are a lot of other metrics that have been introduced, but I think the crucial aspect is to think of what your end goal is. So you want to do unsupervised learning, to do semi-supervised learning, then integrate your unsupervised learning into your pipeline, just like we've seen at the beginning of the talk, and see how well you're doing in terms of classification accuracy. Do you want to do reinforcement learning? Then look how much it's helping your agent learn, and so on and so forth. This makes it harder in terms of papers to compare, but if you care about an end goal, this is the best way to evaluate your model. So now let's look at a few applications. So let's look at a few combinations between models, learning principles, and objectives, and what they allow us to do. So one idea is to use, as we've said, implicit latent variables and GANs, and this is very successful. It can be used to generate samples of high resolution that look like this, trained on very diverse data sets such as ImageNet. And again, here, it's important to stress that modality matters. So this is going to be much harder to do for discrete data such as text. Then there's generative adversarial imitation learning. So taking this idea of the adversarial approach to learn behavior in RL. So if you have expert demonstrations, you can say to your model, well, I want you to learn behavior that is so similar to the expert behavior that a discriminator cannot distinguish between the between the expert demonstrations and what the model is providing. And someone asked, well, is unsupervised learning then useful for other types of learning? Yes, because these kind of basic principles apply also in RL, apply in supervised learning, and so on. And there's also the idea of using explicit latent variable models in representational learning to help reinforcement learning, for example, learn faster or learn a task that it couldn't do before. So this is one simple example where in orange, we have the agent learning from raw pixels. In blue, we have the agent learning from learned representations. And we see that on a simpler task, this makes the difference between having low gradient variance and having, sorry, not low gradient variance, low variance generally. So all curves are learning. Or some solving the task, but way slower than the agent that used representational learning. But if we make the task harder, then using representations makes the difference between learning or not learning the task. So this is really important in reinforcement learning as well. Then there's exploration. Exploration is a really hard problem in RL. So how do you know how to balance exploiting what we've seen and finding something new? This is harder in general, and a very, very big problem. And what we can do is we can train an agent, and we can provide it with additional reward that says, well, I haven't been here before. So we can change our reward structure to provide it a reward bonus that says, if I haven't been here before, please go to this part of the space. Now, the question is, how am I going to measure, oh, I've never been here before? Well, the way you measure that is through a density estimator. So, for example, a density estimator trained by maximum likelihood, something like Pixel CNN. And what that tells you is then, well, this density estimator measures in probability space how likely is it that I've been here before. And if it says, well, I haven't been here, then I just nudge the agent a little bit to go in that part of the state space. And that can make the difference on hard exploration tasks between not learning at all and being able to solve the task. So this is also quite important. Then there's also language. So autoregressive text modeling trained by maximum likelihood, especially with well-tuned neural architectures and large amounts of cleverly chosen data, like it was done in this GPT paper, can lead to representations or models that can then be used for a lot of downstream tasks, such as reading comprehension, translation, summarization, and question answering. So this really allows us to use this idea of unsupervised learning for a lot of text understanding tasks. And then there's the fun examples. Making them fun doesn't mean that they're not important. So this idea here is using adversarial learning to do unsupervised image-to-image translation. So the key here is word here is unsupervised. We're learning to map between images of zebras to images of horses, from paintings of Monet to photos from summer to winter, without having paired examples. And the reason this is important is that it would be impossible to get these pairs examples. Generally, zebras and horses don't really tend to sit as you want them to sit. And for example, if we think of paintings, where Monet painted something, it might be unknown. That specific place might have been completely changed by now. So building this kind of supervised data set of paired examples would be impossible. But using the principles behind adversarial training, like we've seen before, allows this. So it allows us to learn unsupervised how to map between paintings and photos, and also back. And this is a lot of fun, and it also, I can attest that it is a very nice present to give to your friends. If you take a picture of them and make it look like someone painted it, then that's quite a lot of fun. I don't know if they like it. I like to give this kind of presents. So to conclude, you have a lot of choices. Many choices, and it's not necessarily clear which one is right for your application. You have to think very hard of the trade-offs that these have in terms of objectives. We've seen divergence minimization. We've seen adversarial approaches. In terms of models, you can look at explicit or implicit models. So whether or not you want to do direct density estimation, we can look at observed and latent variable models. And the choices, again, depend on your application. And then there's learning. And learning can be easier or can be difficult depending on the choices that you've already made here. And that's it for me. Thank you very much for your attention.
Thank you so much, Mihaela. This was such a fascinating talk. There are a ton of questions. We don't have enough time to go through all of them, but we will just go through just a few. And then we will take all the questions in a doc for Mihaela to answer offline. So great talk. That's the first question. That's how it starts. Do you have experience in the unsupervised extraction of attributes from graph-based structures?
Personally, no. So the honest answer is no. I think there's a lot of work being done there. So there's a lot of methods that now explore this graph structures through graph nets. So that's one of the first place that I would look at.
Great. Good resources for learning about generative models, books or courses that explain the topic in depth.
There are. I think this is best if I take this in writing so that I
Yes.
can actually provide the resources.
Perfect. Yes. So I think this is again from the first, similar to the first question, if you recommend unsupervised for beginners.
I think it's interesting to understand. I wouldn't say that unsupervised is everything. It's really, really important to understand. But for example, as an unsupervised learning I don't know, aficionado, I've also done reinforcement learning because I think that's also important. I've also done supervised learning. So it's important to understand the principles, but it's not the only field out there.
Can we use unsupervised learning for non-stationary distributions? If yes, how?
Yeah, it's a bit hard. So for example, even in the RL example that I've shown with exploration, of course, the distribution kind of changes. There are ways. It's not easy. So for example, even GANs can be thought of as dealing with non-stationary distributions because the generator keeps changing and the discriminator has to adapt to that. So there are ways.
Do you think energy-based and score matching models will be competitive for generation like GANs and inference?
I think energy-based models are definitely having a comeback right now, and it's worth having a look on that. A lot of the challenges that we've seen with sampling and so on are being addressed. So I think keep an eye on this space. I think the next 1 or 2 years are going to be very, very interesting. That's a very, very good question.
Why neural networks are not invertible? Because of Rayleigh pooling. Maybe some NNs are invertible. Because we have all the weights and formulas, why not revert?
Yeah, so because so two reasons. Yeah, ReLU is a very, very simple example. ReLU of -1 equals ReLU of -2. But also, if you think of an MLP as a matrix multiplication, that weight also need not be invertible, right? There are ways to make these things invertible. I can also point to a few papers that have done that.
Great. Can you explain more why reversing a KL lead to the model favoring one rather than both peaks?
Yeah, I can explain this, and I can also maybe make a small drawing for the doc. So the idea is that it goes back to the. Can I present again, just briefly?
Sure.
I can just show that here in the objective. Where did we see the reverse scale? But here it is, just so that I provide. It's not letting me present at the moment. I think it's, so the simple, let me not present. I think the simple intuition is that if you look at the reverse scale objective, it has this expected value under the model of the likelihood of the data. So what it's saying is that generate data that is likely under the distribution, the true distribution. It's not saying cover the whole distribution. So if I have 2 peaks and I'm generating data only here, that is likely under the true data distribution, right? Which is different than the other KL, which is saying the expected value is under the data. So for all data, you have to explain it.
Okay. Practical implications of Wasserstein GANs.
So firstly, I think it opens up this idea of ways to train models using different type of distances and divergences. In practice, it has been used in some papers. I think a lot of the newer state-of-the-art work on GANs focuses a lot on this idea of building the right type of biases into our discriminator. And that's perhaps a bit less related than the loss function itself.
Is language modeling a special case of autoregressive modeling?
Yes. Well, in general, yes. Language models are often models autoregressively because autoregressive models are very suitable for sequential data. And you also don't want to restrict yourself to assuming a particular sentence length. So autoregressive models are very, very flexible like that.
Okay, maybe we just take just one more. Do you think it is possible to learn causal models in a weakly unsupervised way?
Well, we know learning causality from data is not possible without making some further assumptions. So I think I'm not going to say that I'm a causal expert, because I'm not, but this is again another interesting field that I think is going to come up in the next few years, and specifically through allowing us to build better assumptions in our model. So again, coming back to the excellent question about the no free lunch aspect.
Okay, so I think we will stop here, and thank you again, Mihaela. This was such a great talks, and yes, all the answers to the unanswered questions will be provided offline through a doc. And I think there are quite a few questions regarding normalizing flows. Some people were a bit lost about that, but just no worries. The next lecture by Jacek will go more in depth on those topics. So yes, thank you again, Mihaela, and see you all soon for the next lecture. Thank you.
Great. Thank you, everyone. Bye-bye.